Okay, this is the second video on section 16.2 about line integrals. And in this video, I'm going to cover line integral of vector field like f of xy, big F of xy, or f of xyz. Remember in the last video, we did line integral of f of xy, scalar valued function, or f of xyz. But essentially, the idea is the same as this and this. And in this video, we're gonna deal with line integral of a vector field. Situations are slightly different, but quite similar. But in order to give the motivation for this line integral, let's think about this example. Think about this example from physics. Suppose you are given a curve C defined by a parametric equation. R of t is x of t, y of t as usual, some curve on the xy plane with t is between a and b, some particular number a and b. And suppose you are given a vector field. So the function we integrate in this case is going to be actually a vector field. So remember, vector field has two inputs, x and y, and as output, you have a vector on the xy plane. So that means for the output, x component is a function of x and y component is a function of x and y again. Why? By using ij notation, this is written as this. This. Okay. Then now, as I explained in the section on vector field associates to each point on xy plane a vector, and then we can think of a vector field in lots of different ways. But in this case, let's view the vector field as some kind of force field. Force field. So here's a way to think about this situation. Suppose this xy plane is a surface of swimming pool, surface of water, swimming pool. Okay, and then at each point, water is flowing. Swimming pool is flowing. Water is moving, and at each point, the arrow represents the movement of the water. Well, in other words, water is moving. That means at each point on the surface of the water, we have some force acting on the water. And that's what I mean by force field. So you may think of this f of xy, which is given as this vector, as a force acting on the water at each point xy. And then suppose you dip your finger on the surface of the water, and at time t is equal to a, your finger is here. And then you move your finger along the curve like this. Like this. And the t is equal to b. So you move your finger along this curve given by r of t. Then, since you are moving your finger in a moving water surface, water acts on your finger, and that, namely the force field, acts on your finger, and that produces a work in the sense of physics. Then now, then with this situation, the question is this: compute the work done by this force field F when you move your finger from t is equal to a to t is equal to b. From T is equal to A to T is equal to B along C. Okay. Then now, to do this, so here's the answer. Let's remember what is work in terms of physics, in the terminology of physics. Work is force times displacement, as long as you are moving on a straight line. Displacement. So that's what the work is. And the work is a scalar, by the way. So that means if you look at everything here more microscopically, look at it microscopically, meaning you look at everything by using a microscope. The situation is like this. So you look at everything by using a microscope. R of t is viewed as a line. If you look at a very small portion of this line, this curve is no longer a curve, it's a line. And at time t is equal to t, suppose you are here. And then suppose at this point, the force is acting in this way. Our vector f is pointing in this way. Then the actual contribution of the force when you move on this line in this direction is not this entire f, but only the component here along this line, along the curve, along this line. So that's the actual contribution. So this is the actual contribution. From the force. Okay, so then now the question is your finger is here at t is equal to, at some given time t, and then you move a little bit, let's say ds, small displacement ds. So when you move this small displacement ds, this amount of force acts on your finger. So what is that? Well, so work done during this small displacement ds is, like I said, force times displacement. But what's force? Force is this actual contribution. And displacement is ds. So we know what ds is. But what is this actual contribution coming from f in the direction of this? In the direction of this line? Well, let's call this angle theta. Okay. Then here, this one is, well, by looking at this right triangle, you will see that the actual contribution from f is the magnitude of f times cosine theta. That's the actual contribution. But what is this? This one is actually force dot product t. Remember, t is the unit tangent vector of the curve. That's the derivative and the magnitude. You divide by magnitude to make it into a unit vector called a unit tangent vector. Why? Well, because first of all, if you approximate this curve as a line, the vector going like this is r prime of t. And if you normalize it by dividing by its own magnitude, what you get is a unit vector. And since it's a unit vector, if you take the dot product is the magnitude of f times the magnitude of t. times the angle between them. But since this is 1, what we get is this. So that's why we have this formula. So therefore, the actual contribution coming from this force in the direction of r of t is F dot t. Okay, but like I said, F dot t is explicitly written this way. So this is F dot r prime of t divided by the magnitude of r prime of t. Then now, what was ds? Remember, ds is computed as magnitude of r prime of t dt from the previous lecture. So this much is ds from the last lecture, this last video. And then if you cancel those, what you get is just f dot the derivative of t, derivative of r, and dt. So that's the actual work done by the force. And since this is a dot product of two vectors, remember dot product is always a scalar. So this entire thing is a scalar, and you have dt. But strictly speaking, we are looking at the force at each point xy, where xy is parameterized by a curve. So what you do is to basically plug in, strictly speaking, this f means f of r of t. You plug in the parameterization to the vector field, and then dot r prime of t dt. Okay, so therefore, the total work, is obtained by integrating this stuff, f of r of t dot r prime of t dt from a to b. Okay, and then this is the formula for line integral of the vector field f along C. And for this, we often write as just a notation. This way. Integral over C, curve C, of f dot dr. This strange looking notation, but by this, what is really meant is this integral. And this is line integral. Integral of our vector field f along C. Okay, and then if you didn't really understand the rationale for deriving this formula, for this course it's okay. Just know how to calculate the line integral. All right, and also let me just introduce more notations for line integral, for vector field notation. So this strange looking symbol dr, d vector r, is just a shorthand notation for this. It's just a notation. And then, but what do you mean by this? This means, remember, r of t is just a parameterization for the curve. So we have this. All right. And then this is another notation for this is dx dt, dy dt, dt. And then you just distribute the dt over the vector like this. You can cancel dt's. And then what you get is dx dy. All right. So on the other hand, our vector field f, or f of xy to be precise, has two components, p of xy, q of xy, and that, let's just omit parentheses xy, and this is pq. So therefore, here, this one, that's this, is written as what? Well, f dot dr is written as pq dot this dx dy. And so therefore this is p times dx plus q times dy. So therefore, we often write the line integral of the vector field as integral of p of xy dx plus q of xy dy, and then over c. This is just a notation, okay? And then usually a problem of line integral of vector field is given in this way. It looks a little strange, but it's okay. Just a notation. You may think of it as a notation, where x component of the vector field is this, and the y component of the vector field appears dy. So, for example, let's work out an example. Evaluate line integral x squared dx minus xy dy, where c is, once again, this portion of the circle. Circle with radius 1, this circle. So often the time, problem of line integral of vector field is given this way. And how should we do this? Here's the answer. So first you have to figure out the vector field you want to integrate, big F of xy. In this case, x components and y components appear in front of dx and dy respectively. So that means in this case, x component is just whatever you see in front of dx, that's x squared in this case. And the y component is whatever you see in front of dy, that's negative xy. And then you figure out the function you want to integrate, vector field you want to integrate, and then you parameterize the curve. But in this case, curve is just a circle with radius 1. So this is cosine t and sine t. And then t is between 0 and 1/2 because it's a circle, part of the 1/2. Okay, and then to compute line integral, you have to plug into this formula. So what you have to compute is the derivative. You differentiate negative sine t and cosine t. So you differentiate it. So therefore, the given line integral, this one c x squared dx minus xy dy, is obtained as integral of f of r of t. You stick in the parameterization to the vector field you integrate, and then you compute the derivative and take the dot product and integrate with t, and t is from 0 to pi over 2. But what is this? Well, this is 0 to pi over 2. So what you do is to stick in r of t to the vector field you integrate, excuse me, So that means this is x and this is y. And you have to do is just plug in those to x and y's here. So you get the vector cosine squared t and then negative cosine t and sine t. So this is here. This part is here. And then dot the derivative. So derivative is written here. And then what you do is just compute the dot product of those two vectors. And what you get is negative cosine squared t sine t, negative cosine squared t sine t, and dt. And that is equal to 0 pi over 2 negative 2 cosine squared t sine t dt. And then if you work this out, you are supposed to get negative 2/3. And to this is just a calculus one, but to this you have to use u substitution. U is equal to cosine t. Yes. Okay. Then now, essentially, we can generalize this to line integral of a vector field with 3 variables. But I think just I'll work out the example in the next video.